Hello everyone. So this week we are going to start with the chapter 2. Chapter 2 is the application layer. In the previous chapter we learned about the 5 layers of the TCP/IP model, which are starting from the bottom: physical layer, data link layer, network layer, transport layer and application layer. Now the further course is divided as we are going to talk about each layer in detail. What are the protocols, what are the services offered by each layer. So in this book we are going to follow the top-down approach. Top-down approach means we are going to start with the highermost layer, then we are going towards the next lower layers. So the topmost layer of the TCP/IP is the application layer. So in this chapter we are going to discuss about in detail about application layer. What are the applications used at this layer? What are the services offered by the application layer? What are the protocols used at the application layer? So let's start with this. Alright, moving ahead. In this chapter we are going to talk about the first thing that we are going to talk about in general, the principles of the network applications. Then we are going to talk about the protocols that although there are many protocols offered at the application layer, but we are going to talk about only some specific protocols. The first protocol that we are going to talk about is web and HTTP. Then we will discuss about FTP. Then email, electronic mail, then DNS, domain name server. Then we are going to talk about peer-to-peer applications, and the last thing we are going to talk about is socket programming with UDP and TCP. Alright, so let's just have a quick look at some of the network applications that the users, being a user, you must be using or I must be using. All of us are using email very frequently, we are using web very frequently, text messaging, we are using remote login, peer-to-peer file sharing, multi-user network games, streaming applications like YouTube, Netflix, then voice over IP like Skype, real-time video conferencing applications, social networking applications, searching, and the list goes endless. So these are the applications that are offered by the application layer. Now when an application layers give some application, that means some apps to the users, there must be protocols associated with that application. Alright, now let's have a general discussion creating a network application. Suppose you want to create an application, or you have an idea and you want to write a code. So how are you going to create the application? You are going to write a program, that means some software code. Now when you write that software code, after you finish that, that software code will run on different end systems or the hosts. End systems are, for example, a laptop, mobile computer, or a PC. So that application will run on different end systems. Also, that application will communicate over the network. That means it will help the people to communicate, to send and receive messages. And example is something like web server software. It communicates with the browser software. So whenever we are accessing a web page, in that case the server is communicating with our browser software. Browser is a software, for example our Chrome or Internet Explorer or Edge. Now when we are writing a software, we do not take care of the network core devices. For example, if you are writing an application or you are developing a game, you are not taking into consideration that how it will act on routers or how it will act on switches. No, you are just concerned with how the different users will interact with each other and how an individual user can play game on that. So when we are writing a software, we need not to care about the network core devices. We need not to write the software for the network core devices, because the network core devices, for example the router, the switch, the hub, the repeater, they do not run user applications. User applications are run on the end systems by the user. Alright, so this is the pictorial. Okay, now let's move on to the network application architecture. Now before dividing your software coding, before you plan your software coding, you should have an idea about the architectural plan of your application. So the possible structure of the application that you are going to design, it can be either a client server, it can be P2P, which is peer-to-peer, or it can be a hybrid of the client and server and peer-to-peer. That means it can involve both client server and peer-to-peer. Now what is client server, what is peer-to-peer, what is hybrid of client server and peer-to-peer? Let's talk about it. So coming about client and server. Client and server, I think many of you must be familiar with. In client and server model, there is always a host called the server, which services the request for many other hosts. So there is always on host, it services the request for many other hosts, and those hosts are called as the clients. Client host can either be sometimes on or sometimes off, but server is always on. An example is the web application. For example, whenever you are trying to work on any web application like Amazon, or you are trying to run Google, when you type Google, the request goes to the web server. The web server is always on, and the web server services the request from the browser. The browser is running on the client machine. So when a web server receives a request for an object from the client machine, it responds to the client by sending the requested object to the client machine. So whenever you try to open a Google, you send a request to the web server. Web server machine is always on. Web server machine listens to your request and then it responds by loading the object on your machine. Now, in client server architecture, clients do not directly communicate with each other. The clients are not communicating with each other. Also, for the servers, the servers have the permanent IP address, and they are basically the data centers for scaling. Right? So the clients do not directly communicate with each other. For example, in web application, if you are running two browsers, one is Chrome and other one is Mozilla Firefox, the two browsers, they will not directly communicate with each other. And another point to note about client server architecture is that server has a fixed well-known address, which is called as the IP address. So server always has the fixed IP address. Now because server has the fixed IP address, because the server is always on, a client can always contact the server by sending a request packet to the server's address. And some of the I can say like better known or well known applications with the client server architecture, they are web, FTP, telnet, and email. Also, now because client server application, a single server host is not capable of keeping all the requests from its clients. For example, if we take an example of any social networking site, for example Facebook or Instagram or any, the server can quickly become overwhelmed if it has only one server and it is handling all the requests. So for this reason, we have a block of hosts which are sometimes referred to as the data center, and they are often created as a powerful virtual server in the client server applications. So to sum up, we can say that clients communicate with the server. They may be intermittently connected. Clients have the dynamic IP address. The IP address of the clients can change because since the clients are moving, clients do not communicate with each other directly, right? All right. So moving ahead. Okay. Now we talk about peer-to-peer architecture. Peer-to-peer means there is no server. There is no concept of something like server or the client or something like a master or a slave. No, there is no always on server. So there is no always on server, and the end systems are communicating directly with to each other. For example, if you can see in the picture, the car is communicating with the laptop. The laptop is communicating with this PC. This PC is communicating with the laptop over here. So the end devices are communicating with each other. Peer request service from other peers. So basically this peer will request for a service from the other peer, and the other peer will provide a service to the other peers. Peers are intermittently connected and they can change the IP address. So if you see this laptop is connected to this PC through some link, but this can always move. So peers do not have the fixed IP address. They can change their IP address. That's why their management is quite complex. The advantage of peer-to-peer architecture, it's highly scalable, but disadvantage at the same time is it's quite difficult to manage. Then we talk about a hybrid of client server and peer-to-peer. There are some applications which use both client server and peer-to-peer architecture. So for example, voice over IP, Skype is an example of hybrid application which uses both client server and peer-to-peer. So voice over IP is a peer-to-peer application. Now it has a centralized server, so it finds the address of the remote party. If you have used the Skype, first of all, when you log in into your account, you find the name of the person to whom you want to converse, with whom you want to talk. So that address is found by making a connection with the server. So there is a centralized server for finding the address of the remote party and client. But when you are making a connection, when you are making a Skype call, that is a client to client connection. It's a direct connection. It's not through server. Same thing is with the help of the instant messaging, IM, like your WhatsApp messengers, Facebook Messenger or any other messenger. So chatting is between the two users is peer-to-peer. But there is a centralized server. Client is present for the detection or location or for registering the users, finding the users. So once you add a user, after that when you chat, when you send the messages, that is peer-to-peer. So there is a centralized service. User registers its IP address with the central server when it comes online, and the user contacts central server to find out the IP addresses of its contacts. So the basic use of the server is to find out the contacts. After finding out the contacts, the message that you send or the conversation that you make, it's peer-to-peer. Now let's talk about process communication. Now there is a difference between program and process. When a program is running on a host machine, on any end machine or any host machine, that is called as the process. So for example, when WhatsApp is running on your machine, that is called as the process. Now within the same host, two processes communicate using inter-process communication, which you might have learned in the operating system. So processes communicate with each other. Now processes in different hosts communicate by exchanging messages. So when the processes are running on the same end system, they can communicate with each other with inter-process communication using rules that are governed by the end system. Processes on two different end systems, they communicate by exchanging the messages across the computer. So we have a sending process and a receiver process. A sending process can create and send a message to the network, whereas a receiving process can receive these messages and it can possibly respond to the sending messages, right? Now coming to the client and the server. What is a client process and what is a server process? Client process, in case of client server, client process is a process that will start the communication, whereas server process is a process that waits to be contacted. Also applications with peer-to-peer architectures, they have client process and the server process. So client process and the server process in peer-to-peer applications is initiated when we want to look for a address or when we want to look for a contact. Now let's talk about sockets. So what is a socket? Now from our discussion, what we have discussed until now, we notice that most of the application, it consists of a pair of communicating process with the two process in each pair sending messages to each other. So any message sent from one process to another must go through the underlying network. If we are sending a message, for example, from this machine to this machine, now the message will be sent through the underlying network, whatever the network we have. So a process sends messages and receives messages from the network through a software interface, which is called as the socket. So what is a socket? Socket is an interface between a software or a process in the application layer and a transport layer in the network. So software is just this interface between the application layer and the transport layer. It's an application layer between a software or a process in the application layer and the transport layer in a network. Now processes sends and receive the messages to and fro from its socket. So processes, they use the socket to send or receive the message. Let's consider an example to understand the processes and the socket. For example, a process is just similar to your house. You live in a house, so that is called as, let's assume it is called as a socket. Now, it is called as the process. Now, socket is analogous to its door. So, when a process wants to send a message to another process on another host, it shows the message out of its door. So, for example, in your house, for example, if we consider it as a process, if anyone wants to enter into your house or leave from your house, it must pass through that door. So similarly, socket is just like a door in the application layer. Any message that is sent from the application layer or received to an application must pass through that socket. So socket is analogous to a door. Sending process shoves message out of the door, and sending process relies on the transport layer infrastructure on the other side also to deliver the message to the application layer at the receiving process. So this sending process assumes that there is a transportation infrastructure on the other side of its door also that can carry the message to the destination process. After the message arrives at the receiving host, the message passes through the receiving host process door, which is called as the socket, and the receiving process then takes up the message. Now this process or the application is controlled by the application developer, whereas the other layers, these are controlled by the operating system. Now socket is actually an interface between the application layer and the transport layer on any host. It is sometimes also referred to as the application programming interface between the application and the network, because socket is the programming interface with which network applications are also built, which we are going to learn later also. Alright, so addressing a process. So to receive a message process, to receive the messages, a process must have some identifier. We talked about this in the previous lecture, identifier of the process, which we called it as the port number also. Port number is actually used at the transport layer. So to receive message, process must have the identifier. As we know that any device or any host, it has an IP address, and that IP address is 32-bit. Any host device has a 32-bit IP address. Now, does this mean that IP address of a host on which the process is running is you can say enough for identifying the process? The question is the IP address of the host machine where the process is running. For example, WhatsApp is running on your phone. So is the IP address of your phone enough for identifying a process? No. The example is no, because on your phone there can be many processes which are running. So IP address is not sufficient for identifying a process which is running on your machine. There must be some another identifier, some another unique entity to identify the process. So no, because many processes are running on the same host machine. So identifier for a process includes both IP address and the port number. So what is the identifier for a process? Identifier for a process includes both IP address and a port number. So for example, if your process, you are using HTTP application, the port number is 80. And for example, the IP address of your machine is 10, 10, 10 and 1. So both these are necessary to identify a process. So identifier should include both IP address and the port number associated with the process on the host. Now the combination of the IP address and the port number, this is called as the socket address. This is called as the socket address. So the combination of IP address of the host and the port number of the process, both when they are combined, that is called as the socket address. So for example, port numbers are for the HTTP server, it is 80, for mail server it is 25. We have specified port numbers for all the applications which I am going to discuss in a while. Now to send a HTTP message to, for example, this web server, let's assume IP address of the web server is this and the port number is this. So the identifier of the process will be combination of the IP address and the port address, which will be called as the socket address. Now application layer protocol, what does it define? It defines types of messages that can be exchanged. For example, it can be a request message, it can be a response message. Message syntax, because there are many fields in the message. So what is the meaning of each field? So how the fields are delineated and what are the fields in the message? Meaning is identified by the semantics. Syntax tells us what are the fields and how the fields are delineated, that means separated from each other. That is called as the syntax. Semantics means meaning of each field. Whatever the fields are defined in the syntax, their meaning is called as the semantics. Then we have the rules for when and how the processes should send and respond to the message. So what does application layer protocol defines? It defines 4 things. First thing is types of messages exchanged, message syntax, message semantics, and rules for the processes to communicate with each other. Alright, now application layer protocol defines types of messages exchanged, message syntax, semantics, rules. Now there are public domain protocols which are defined in all RFCs. They allow the interoperability also, and some of the public domain protocols are HTTP and SMTP. There are proprietary protocols also. Proprietary protocols are developed by the individual organizations or someone is in charge of that. Example is Skype. Now, as we learned in the previous chapter, when we were doing the chapter 1, we learned that each higher layer uses the services of the lower layer, right? Or we can say each lower layer offers some services to its upper layer. Now, application layer is the topmost layer. A transport layer is the layer below it. So what are the services that application layer uses from the transport layer? Or in other way around, we can say that what are the services that a transport layer offers to the application layer? So what transport service does an application need? What are the services from the transport layer an application will require? First and foremost thing is data reliability. It requires reliable data transfer. Some applications, for example, file transfer, web transactions, especially your money transaction, they require 100% of reliable data transfer. So it is the responsibility of the transport layer to provide reliable data transfer. So to support these applications, something has to done to guarantee that data sent by one end application is delivered correctly and completely to the other application. So if a protocol provides such guaranteed data delivery, it is said to provide a reliable data transfer. And once this is one of the service that transport layer can provide to the application layer, which is process to process reliable data transfer. So when a transport layer protocol provides this service, the sending process can just pass its data to the socket and know with complete confidence that data at the other side will arrive without any errors. There are many other applications also, for example audio, that can tolerate some loss. They are called as the loss tolerant application. So when a transport layer protocol does not provide reliable data transfer, data sent by the sending process may never arrive at the receiving process, or it may arrive at the receiving process with some errors. So these are called as the loss tolerant applications, and multimedia applications are an example. Next is the throughput. Now in chapter 1 we learnt about the concept of the throughput. We learned about the throughput, which means that the rate at which sending process can deliver the bits to the receiving process. So the rate at which a sending process can deliver the bits to the receiving process. Some applications, for example multimedia applications, they are throughput sensitive applications. They require minimum amount of throughput to be effective. They are called as the bandwidth sensitive applications. Let's take an example of such applications. Let's talk about the internet telephony applications. For example, if an internet telephony application requires any X data rate, let's assume 32 kilobits per second. It requires the data rate. It needs to send data into the network and have data delivered to the receiving application. If the transport layer protocol cannot provide this throughput, the application would need to encode at a lower rate, or it should not use that application. Since half of the needed throughput is of little or no use to this internet telephony applications. So these type of applications are called as the bandwidth applications. Other applications are elastic applications, which make use of whatever throughput they get. For example, email applications and file sharing applications. So bandwidth sensitive applications have specific throughput requirements, whereas elastic applications can make use of as much or as little throughput as it happens to be available. Examples are email, file transfer, web transfer. They are all the elastic applications. Okay. The next important service that transport layer should provide is the timing. A transport layer can also provide timing guarantee. As with the throughput guarantees, time guarantee can come in many shapes and many forms. For example, time guarantee might be every bit that the sender sends into the socket arrives at the receiver socket in no more than 100 milliseconds. Such a service would be appealing to the interactive real-time applications such as internet telephony, virtual environments, teleconferencing, multiplayer games, which require tight timing constraints. So these are some of the applications which really require timing constraints. Long delays in the timing, for example in internet telephony, for example, can result in unnatural pause in the conversation. Imagine you are talking to your friend using your phone, and whatever you say, it is done in encoding. Encoding is done in the form of the bits. There is it is taking a long delay to reach at the other end. So in that case, there will be a pause in the conversation. And same in case of multiplayer games or virtual interactive environment. Long delay between the action and seeing the response from the another player makes the application very boring or less realistic. And the last thing which a transport layer must offer to an application layer is the security. Security can be like encryption. For example, in sending host, transport layer can encrypt all the data by sending the process and receiving the host, and transport layer can decrypt the data before delivering the data to the receiving host. Such a service will ensure confidentiality between the two processes. A transport layer can also provide other services such as endpoint authentication. Alright, these are some of the transport service requirements for the common applications. Application name is given, data loss, throughput, and the time sensitive. You can go through all this. Now let's talk about Internet Transport Protocol services. The two protocols which are used at the transport layer, we learnt in the previous chapter also. The two protocols that are there in the transport layer, they are TCP and UDP. Now, what does TCP offers to the application layer and what does UDP offers to the application layer? TCP offers reliable transport, flow control, congestion control, and what it does not provide, we will learn about it. It provides reliable transportation between the sending and the receiving host. So the communicating processes can rely on TCP to deliver all the data sent without error and in the proper order. When one side of the application passes a stream of bytes to the socket, it can count the TCP to deliver that amount of bytes to the other layer. TCP also provides flow control. That means sender won't be overwhelmed by the packet. Sender won't overwhelm the receiver with a flood of the packets. The third service that TCP offers is the congestion control. It will throttle the sender when the network is overloaded. So congestion control mechanism, it's a service for the general welfare of the internet. So congestion control throttles a sending process. It can be client or the server when the network is congested between the sender and the receiver. But TCP does not provide timing, minimum throughput guarantee, and the security. So these are the things that TCP does not provide. TCP is the connection oriented. It takes time for setting up the connection between the client and the server process. So these are the two, you can say, disadvantage. Now let's talk about UDP. UDP provides unreliable data transfer. That means if any application is using UDP, there is no guarantee that the data will be delivered as it is to the receiving process. That means what is sent is what is received is not guaranteed by UDP. UDP also does not provide reliability, flow control, congestion control, timing, throughput guarantee, security, or the connection setup. So, the question is, why do we need a UDP? UDP is actually a faster protocol. It's a lightweight transport protocol. It's a connectionless protocol. So the applications which require faster data transfer, they use the UDP for their application. So it is basically a faster and it's a connectionless protocol. Alright, moving ahead. Some of the applications which use the underlying transport layer, for example, email uses TCP, a remote terminal access uses TCP, web file transfer they use TCP, multimedia can use TCP or UDP, internet telephony can use TCP or UDP. Alright, so here we complete our 2.1. Which is principles of network applications. Now we start with another important protocol, which is web and the HTTP. All of you are familiar with that, web and the HTTP. Let's first of all review the web and the HTTP. You are familiar with what is a web page or a web document, what is a URL, you are familiar with all this. Web page or a web document, it consists of objects. What can be an object? Object can be an HTML file, it can be image, it can be Java applet, it can be audio file, or it can be anything. Web page consists of basic HTML file which includes many referenced objects. So in that HTML file, we make use of the objects to which we provide some reference. Each object is addressable by a URL. The full form of URL is Uniform Resource Locator. So for example, www.ucj.com, and for example, we are given over here www.someschool.edu/somedepartment.pic.gf. So the first part until here, edu tells us the host name, and the last part tells us the path name for that object. All right. So HTTP. We just have an overview of the HTTP. HTTP stands for Hypertext Transport Protocol. It's the application layer protocol which is used by the web. It follows the client-server model. So client is our browser. For example, Chrome or Firefox or Safari. So browser that requests and receives. So using HTTP protocol, your browser sends a request to the server and server responds by loading or sending the requested object. Web server sends using HTTP protocol all the objects that are requested by the client. So for example, we have a PC running on the using Firefox browser, iPhone using the Safari browser. So they can request for any page to the server, and server will respond to their request by uploading the specific page. So PC can send HTTP request for any, for example, ucj.edu.sa, that's a HTTP request, and the server will load that page, the requested page, on the PC, on the client's PC. That is called as the HTTP response. Same way, for example, iPhone is requesting for www.google.com, that is HTTP request, and server will respond by loading the Google page on the client's iPhone. So HTTP has two messages, HTTP request and HTTP response. HTTP request is sent from client to the server, and HTTP response is sent from server to the client. Alright, now we learned in the previous slide also that HTTP uses the TCP protocol of the transport layer. So TCP protocol of the transport layer is used by HTTP. So how the connections are made by TCP? Clients initiates connection to the server at port number 80. HTTP uses port number 80. The port number for the HTTP is 80. So the client is your web browser. It initiates the TCP connection to the HTTP server by using the port 80. Server will accept the TCP connection from the client. Now server will accept that connection, and the HTTP messages, application layer protocol messages, they are exchanged between the browser is HTTP client, and the web server, which is the HTTP server. After exchanging the messages, TCP connection will be closed. So TCP follows the three phases for the connection setup. First is request, then data transfer, and then connection termination. So over here, client, you send a message to the TCP for uploading some page. HTTP messages are exchanged between client and the server, then connection is terminated. Okay, HTTP is stateless. Stateless means server maintains no information about past client requests. Server does not maintain any information what the client has requested previously. Now, there are protocols that maintain the state, but they are very complex. Past history must be maintained, and if the client or the server crashes, their views of the state may be inconsistent and must be reconciled. When we say it's a stateless protocol, we mean that, for example, you have requested for ucj.edu.sa. Server will respond by loading the page of UCJ. After a few seconds, you request for the same page again. Now the server will not respond by saying that it just served you with that object. Instead, the server will resend that object as it has completely forgotten what it did earlier. So because the HTTP server maintains no information about the clients, it is called as the stateless protocol. Alright, so moving ahead. Now, HTTP connections can be persistent or it can be non-persistent. We are going to talk about what are persistent connections and what are non-persistent connections. So, persistent and non-persistent connections. Let's talk about non-persistent connections. Now, in many internet applications, client and server communicate for long time. When the client makes a series of requests and the server responds to those requests. When the client and server interaction is taking place over the TCP, the application developer needs to make an important decision. Should each request and response pair should be sent over a separate TCP connection, or should it be sent over the same TCP connection? Now, this is the most important point. When the client and server are interacting with each other for multiple requests, now application developer, the one who has developed or written the code or developed the application, should decide that request and response should communicate over same TCP connection, or different TCP connections should be opened for request and response pair. In the former approach, the application is said to use non-persistent connection, and the later one is the persistent connection. So, at most one object can be sent over TCP connection. Connection is then closed. Connection is then closed. That means request and response pair, they are sent over separate TCP connections. That is called as the non-persistent HTTP. So if we are downloading multiple objects, we require multiple connections. Now, what is persistent? Persistent is the corresponding request and response can be sent over the same TCP connection. So multiple objects can be sent over the single TCP connection between the client and the server. That is called as the persistent HTTP. Okay, so let's start. Check the working of the non-persistent HTTP. Non-persistent means a separate TCP connection is used for the pair of the request and response pair. Alright. Now we are going to understand this non-persistent HTTP with the help of this URL, which is given as example in your book, someSchool.edu/somedepartment/home.index. So how does the non-persistent HTTP connections are done? Alright, so in this case, the client, which is the browser, it will initiate the TCP connection with the help of the HTTP server and using the port number 80. The request is sent on the network to the server at the host someschool.edu, waiting for the TCP connection at port number 80, and it accepts the connection and notifies the client. Right, it notifies the client. So this was the request, this was the response is sent. Now the client sends HTTP request message which contains an URL into a TCP connection socket. So again connection is open. Connection socket message indicates that it wants the home page of this some department/home.index. So this is sent. Now HTTP server receives this request message. It forms a response message containing that requested object, and then it sends the message into its socket to the client. All right. Then what happens? Then HTTP closes the TCP connection. HTTP closes the HTTP server tells TCP to close the TCP connection. Now the HTTP client receives the response displaying containing HTML file parsing. It has 10 referenced object. Now these steps 1 to 5 are repeated for each of the 10 JPG object. In the last step, the HTTP client receives the response message. The TCP connection terminates. Message indicates that encapsulated object is an HTML file. Client will extract the file from the response, checks the HTML file and finds there are 10 objects. So the first 5 steps are then repeated again for those 10 JPEG objects. This is called as the non-persistent. So as the browser receives the web page, it displays the page to the user. Two different browsers may interpret a web page in somewhat different ways. HTTP has nothing to do with how a web page is interpreted with a client. So the steps what we have discussed now, they tell us the use of non-persistent connection where each TCP connection is closed after the server sends the object. So the connection does not persist. Non-persistent means connection does not persist for other objects, and the TCP connection transports exactly one request message and one response message. Now let's talk about the RTT, which is the round trip time, the time taken by a packet to travel from a client to the server and from to the back. So RTT, round trip time, is a time for a small packet to travel from a client and to the server back. So if you see, for example, between when request is sent from client to the server response is received from server to the client, that is 1 RTT. Same thing, file request for file is sent and the file is transmitted, that is another RTT. So 1 RTT is used to initiate the TCP connection between client and the server. 1 RTT for the HTTP request and the first few bytes of the HTTP response to return. So this is 1 RTT for setting up the connection. This is 1 RTT requesting the server to send the file, and few bytes of the file are sent to the client, plus the file transmission time. In non-persistent HTTP, the response time is 2 times RTT, 2 RTT. 1 RTT for connection setup, second RTT is for sending the requested object, plus the time taken by the file to be transmitted. So 2 RTT plus file transmission time is the response time for a non-persistent HTTP. Alright, now let's talk about some issues related to the non-persistent and persistent HTTP. Non-persistent HTTP, it requires 2 RTTs per object, which is overhead of each TCP connections, and browsers often open parallel TCP connections to fetch the referenced objects. But with the persistent HTTP, server leaves the connection open after sending the response, and subsequent HTTP messages between the clients and the server can be sent over the same TCP connection. So client sends a request as soon as it encounters the referenced object. So approximately or as little as 1 RTT is required for the referenced object. So the basic difference lies in the response time. Non-persistent HTTP takes longer response time as compared to the persistent HTTP. Now response status, when the server replies with a response message to the client, there are certain response status code. You might have experienced these HTTP response status code. For example, file not found, which is 404, or 301, which is moved permanently. So a few sample codes are, although there are many more, but we have just a few sample codes to be discussed over here. First one is the sample code 200 stands for OK, which means request has succeeded and a requested object is there in the message later. 301 is moved permanently, that means object has moved to some another location or another URL. 400 is bad request, request message is not understood by the server. 404 is not found, requested document is not found on the server. 505 is HTTP version is not supported. Now let's talk about cookies, user server states. Okay, so let's talk about what are cookies. Many websites use cookies. So first of all, a little background on the cookies. If you can recall, we just mentioned in few slides before that HTTP server is stateless. That means it does not keeps the state of the clients. This simplifies server design and has permitted the engineers to develop high performance servers that can handle thousands of TCP connections. But it is desirable for a website to identify the users, either maybe because server wishes to restrict user access or it wants to serve the content as a function of the user identity. For this purpose, HTTP uses cookies. Cookies allow sites to keep track of users. So cookies, they allow the websites to keep track of the users, and most of the websites, they use cookies. Now, cookie technology has 4 components. The first component is a cookie header. So cookie header line in the HTTP response message. So cookie header line of HTTP response message. Second is cookie header line in next HTTP request message. Third is a cookie file kept on the user's end system and managed by the user's browser. Last one is the backend database at the website. So these are the 4 components of the cookie. Now to understand cookies more better, let's consider an example. Let's consider an example, a person ABC, or as given in your book, Susan, always access internet from PC. So a person is always accessing internet from the PC. The person is visiting the specific e-commerce site, can be Amazon, can be eBay, or can be any other site for the first time. Right, for the first time. So when the first HTTP or the initial HTTP request comes at the site, what the site will create? Site will create 2 things. First is the unique ID. Second is entry in the backend database for that ID. So the 2 things that are created when you send any HTTP request for the first time, a unique ID and entry in the backend database for that ID. Right? Now let's understand it more better. For example, we just talked about this. So let's assume this is a client and this is a server. Now usual HTTP message is sent to the server. Let's assume that the server is Amazon. So when the first request is sent to the Amazon will create 2 things. First is it will create a user ID, let's assume 1678, and it will create an entry for this ID in the backend database. Now server also sends a response, and with the response it uses this cookie value 1678. Now this cookie value will be stored on the client's system. Then again, next time when the client sends the usual HTTP request message, that HTTP request message will carry the cookie also with the number 1678. Now that server recognizes the client by using this cookie and takes the cookie specific, accesses the backend server and takes the cookie specific action, and usual HTTP response message is sent to the client. So let's assume that Susan returns to Amazon site 1 week later. The browser will continue to put header cookie line with the HTTP request message. The header line cookie 1678 the browser will put in the request message. Amazon also recommends products to Susan based on the web pages she has visited at the Amazon in the past. So now when the message is sent to the server after 1 week later, this cookie will be included in the HTTP request message. Server will accept this message, access the backend database and take the cookie specific action. Now let's assume that Susan has also registered with Amazon, providing full name, email address, postal address, credit card information. So Amazon can include this information in its database, thereby associating Susan's name with the identification number and all the pages that person has visited in the site in the past. So this is how Amazon and the other e-commerce sites provide one-click shopping. So when Susan chooses to purchase an item during a subsequent visit, the person does not need to re-enter the name or the credit card or the address again. So this is how the cookies can be used to identify a user. The first time a user visits the site, the user can provide a user identification, can be the name. During the subsequent sessions, the browser passes a cookie header to the server, thereby identifying the user to the server. So this way the server identifies the users. Cookies can be used to create a session layer on the top of the stateless HTTP. So for example, when a user logs into a web-based email application such as Hotmail or Gmail or any other, the browser will send the cookie information to the server and allowing the server to identify the user throughout the user's session with the application. So this is how the cookies work. What cookies can be used for? Cookies can be used for authorization, for shopping cart, for recommendation, for maintaining the user's session state, which is web email. How to keep the state, protocol endpoints maintain the state at the sender and receiver over multiple transactions, and HTTP messages, they carry the state by using the cookies. Now let's talk about cookies and privacy. Cookies permit sites to learn a lot about you. You may supply your name and email sites and the email to the sites. So they can learn a lot about the person. Another thing in this topic, I think it's the last thing for HTTP, which is the web cache or the proxy server. Now the goal of the HTTP is to satisfy the client request without involving the original server. Now web cache is also called as the proxy server. It is actually a network entity that satisfies the HTTP request on behalf of the original server. Web cache has its own disk storage and it keeps the copies of the recently requested objects in this storage. For example, a user's browser can be configured so that all the HTTP requests are first directed to the web cache. Once a browser is configured, each browser request for an object is first directed to the web cache, and if the page is not found in the web cache, and then to the original server. So user sets the browser web access via cache. Browser sends all the requests to the cache. So whenever a page needs to be loaded or searched, the request will be sent to the web cache or to the proxy server. Cache will return the object. Now what this proxy server will do, if that object or that web page is present in the proxy server, it will return or load that page on the client's computer. It will return that object to the client. But if that page or object is not present in the cache, cache will request the original server. Original server will return the object to the proxy server. Now proxy server will store the copy of that page in its memory and then return that page to the client. So HTTP request is sent. Alright, so HTTP request is sent. If that page is found on the proxy server will return. If that page is not found on the proxy server will request the original server. Original server will send that page to the proxy server. Proxy server will store a copy of it and then load that page on the client's machine. This is how the web cache works. Just like your cache memory, which you might have learned in the computer architecture. So browser establishes a TCP connection with the web cache, sends the HTTP request. Web cache checks if it has a copy of the object. If it has, it will return that object with the HTTP response message to the client browser. If the web cache does not have the object, it will open a TCP connection with the original server. Web cache then sends the HTTP request for the object from the cache to the server TCP connection, and after receiving this object, original server sends the object with the HTTP response message to the proxy server, and when the proxy server receives the object, it stores a copy in its local storage and then sends a copy with the HTTP response message to the client browser. So just like your cache memory works, same way the proxy server or the web cache works in the HTTP. So cache acts as both client and a server. How it acts as both client and a server? It serves for the request originating from the client and also client to the original server. It acts as a client when the page is not found in it, so it requests the server. At that time, it is acting as a client. It is acting as a server when the page is there and some browser has requested for that page. Typically, cache is installed by the ISP, which is Internet Service Provider. It can be university, company or residential ISP. So what are the advantages of web caching? Same as the cache memory, it reduces the response time for the client, reduces the traffic on the access link. This is the last topic, 2.3 file transfer protocol, which I am going to talk about in my lecture. The other points will be talked in the next lecture. So let's talk about FTP, file transfer protocol. What is a file transfer protocol? So file transfer protocol, it's a protocol which helps in transferring the file to and from the remote host. It follows the client server model. Client side which initiates the transfer and server is the remote host. FTP server runs on port number 21. So the server port used by the FTP server is 21. Now how does the FTP works? Let's understand this figure. The user interacts with the FTP with the help of the FTP user agent, which we call it as the FTP client. Now the user first of all provides the host name of the remote host to which it wants to contact, causing the FTP client process in the local host to establish a TCP connection with the FTP server in the remote host. After this, the user provides the user ID or the user identification and the password, which are again sent over the TCP connection as a part of the FTP commands. Once the server has authorized the user copies one or more files from the stored in local file system into the remote file system. HTTP and FTP. You can use HTTP also, you can use FTP also for both file transfer protocol, and they have common characteristics. For example, they run both on the top of TCP. However, application layer protocols have some important difference, and the most important difference is that FTP uses two parallel connections to transfer a file. One is a control connection and a data connection. Control connection is used for sending the control information between the client and the server, such as identification, password commands to the remote directory, and data connection is used to send a file. Now, because FTP uses a separate control connection, FTP is set to send its control information out of band. So I have just explained this. They are used for file transfer, and the difference is FTP uses two parallel connection, two parallel TCP connections, one for transferring the control and data. Control is used to exchange information like username and password, and data actually transfers the file and the data. Now, FTP client. Now, how does it happens? FTP client contacts the FTP server using the port number 21 and using the TCP connection. Client authorized over client is identified or authorized over control connection. Now client will browse the FTP directories, send the commands over the control connection. When the server receives file transfer command, server opens another TCP connection for transferring the file to the client. So it opens second TCP connection, and it is opened at the port number 20. So port number 20 is used for data connection and 21 is used for the control connection. After transferring one file, server closes the data connection. Now server will open another TCP data connection to transfer another file. So that's why control connection is out of band and data connection is in band, because it sends request and response into same TCP connection that carries the transferred file. It is said to be in band. So FTP server maintains the state, it maintains the current directory and the earlier authentication of the user also. Okay. Sample commands, response messages or the commands that can be used by FTP. They are sent as the ASCII text over the control channel. This is the command user followed by whatever is the username, pass followed by the password. List is to return the list of file. RTR file name, it is used to retrieve the file. Store, it stores the file on the remote host. Return codes, which are the status codes and the phrases. 331 is username okay, password required. 125, data connection is already opened and transfer started. 425 is can't open data connection, and 452 is error writing into a file. So these are some of the sample return codes. Alright, I will finish my first lecture for this week over here. The rest of the protocols I will talk about in the another lecture, and thank you so much.